So now we get to the crux maneuver, because what we're going to do when we integrate a function over a finite element space is we're going to visit each cell in turn and access the data on that cell. So that in particular means that for each finite element function space, we need to define a function m, which as a function of elements produces the list of degrees of freedom on that element in this order. Right? So this is the global degrees of freedom. So more or less a set of random numbers, but they need to be in the order that corresponds to this, so that all of our code which works locally hits the right degrees of freedom. And this is a little bit tricky because we've got lots of levels of indirection going on here. So we're looking at maps through maps through maps. So actually, as a practical matter then, this is for a given finite element function space, this is a function which takes an element and produces a vector. And what is more, the value of this function depends, among other things, on the structure of the mesh. And the structure of the mesh could be pretty much literally anything. So for what we call an unstructured mesh, a mesh that is arbitrary, there isn't a formula for this guy. So the way we have to implement this mesh is by constructing a lookup table which implements the function. And because it's a function which takes in one number and gives you out an array of numbers, that lookup table is effectively a two-dimensional array. Right? You have one row for each element, and that row consists of the values of the global degree of freedom numbers on that element. That's how this guy works out. So that really means that what I really said is that this row of this guy is equal to that set over there. So how do I do that? Oh, I've called this, let's try and be consistent with the notes, I've called this C for cell. It's the index by cell. So the way I construct this then is by visiting the local topology, looking up the local topology for each entity in turn, and setting the entries in here that correspond to the local topology, and setting them equal to the global entities that are corresponding to that local topology. So this is equation 4.2, which is the crunch of this. So what I'm going to do, let me start over here because this is going to get a bit long, is I'm going to construct for cell C, for entries E delta epsilon, so E is the entity node list, it's this guy, and delta epsilon is going to take all of the dimension entity values in turn. So I'm going to walk over this set. So delta will take the value 0, 1, 2, in this case. Epsilon will take the values when it's 0, 0, 1, 2, when it's 1, 0, 1, 2, and when it's 2, 0. Oh, I missed a thing in there. Right, so that's going to set particular columns of this guy. And what do I put in the right-hand side? I put in the global numbers associated with the global entity corresponding to that local entity. So how do I get the global entity corresponding to a local entity? That's what the adjacency function does. So what I'm going to do is I'm going to say that the right-hand side is equal to G of, and it will be delta comma I up to G of delta comma I plus n delta, right? So this is the array which is that long, starting at this global number. So the one thing I'm missing is a value for I. So delta is whichever sort of entity I'm filling in now. And I must be the global entity corresponding to the local entity delta epsilon. And I use the adjacency function. So I write I is equal to the adjacency of, and it's the dimension of the current cell, 2 in this case, delta, because I'm looking at things of dimension delta, epsilon. Have I got that right? Oh, C epsilon. Right, so if I just put adjacency dim C delta C, I get the vector of all of them, but I want the epsilonth one out of that vector. So that's it. Actually, this is one of these things where it's somewhat tricky to understand what's going on. When you've understood what is going on, you sit down and you write a very, very, very small number of lines of code.